Picture the universe not as an empty void, but as a treasure chest overflowing with cosmic secrets we've only begun to crack open. Every time we point our telescopes deeper into the darkness, space throws another curveball our way, revealing phenomena so bizarre they rewrite the textbooks. Just when we think we've got it all figured out, the cosmos laughs and says, "Think again." And that's exactly what's happening right now. Scientists are uncovering mind-bending discoveries at a pace we've never seen before. Strange celestial objects, unexplained energy bursts, even hints of realities beyond our own. It's like the universe is teasing us with a trail of breadcrumbs, each one leading to something even more astonishing than the last. Take a moment to let that sink in. We're living in an era where space isn't just a distant expanse of stars, it's a living, breathing mystery, unfolding in real time. Imagine standing at the edge of an uncharted forest, where every step forward reveals creatures you've never seen, sounds you can't explain, and rules of nature that don't quite add up. That's where astronomy is right now, and the best part, you don't need a PhD to feel the thrill of discovery. These aren't just breakthroughs for scientists, they're invitations for all of us to look up and wonder. So what's waiting out there in the cosmic shadows? From rogue planets drifting alone in the darkness to galaxies that defy the laws of physics, the universe is serving up surprises that stretch our imaginations to the breaking point. Some of these discoveries could change everything we know about reality itself, like cosmic threads weaving through space or black holes behaving in ways that shouldn't be possible. And that's just the beginning. Buckle up, because we're about to dive into 25 of the most jaw-dropping space phenomena recently uncovered, each one a reminder that the universe is far stranger, far more beautiful, and far more mysterious than we ever dared to dream. Imagine staring at a radio telescope's data and seeing something that shouldn't exist: colossal rings of energy floating in space like cosmic smoke signals, so vast they could swallow entire galaxies. That's exactly what happened when astronomers first spotted odd radio circles, or ORC. These ghostly halos, glowing faintly in radio waves, stretch across millions of light years, dwarfing everything in their path. But here's the twist: no one knows what's creating them. At first, scientists thought they might be remnants of supernova explosions or the echoes of supermassive black holes. But the numbers didn't add up. These rings are too symmetrical, too perfectly round, and they don't match any known celestial event. Some researchers even floated the idea of alien megastructures, though that's more science fiction than science. The leading theory now: a shockwave from something unimaginably powerful, like a collision of black holes or a burst of star formation so intense it sent ripples through the fabric of space itself. What makes ORCs even stranger is that they're practically invisible in other wavelengths of light. You can't see them with optical telescopes, only radio waves reveal their haunting presence. It's like finding fingerprints at a crime scene, but with no suspect in sight. And because they're so faint and scattered, studying them is like trying to trace the outline of a shadow. Every new observation only deepens the mystery, leaving astronomers with more questions than answers. One thing's certain: ORCs are a cosmic wake-up call, reminding us just how much we still don't understand about the universe's most hidden corners. Could these eerie circles be the aftermath of events we've never witnessed before, or are they hinting at entirely new physics, something beyond our current grasp? Whatever they are, ORCs prove that space still holds secrets we're only beginning to uncover, and that's what makes them so thrilling. They're not just anomalies, they're invitations to rethink everything we thought we knew. Deep in the cosmic archives, astronomers have uncovered something extraordinary: ghostly galaxies that shouldn't exist, yet have been hiding in plain sight. These aren't your typical star-filled spirals or blazing clusters. They're cosmic fossils, relics from the universe's infancy, dominated by an invisible force, dark matter. Imagine stumbling upon a prehistoric creature perfectly preserved, its bones telling a story no one had heard before. That's what scientists felt when they first detected these ancient, shadowy galaxies, structures so faint they'd been overlooked for decades. What makes them so bizarre? For starters, they're barely visible. Most of their mass comes from dark matter, the mysterious substance that makes up about 85% of the universe's matter but doesn't interact with light. Their stars are few and far between, scattered like dust in the wind. Some of these galaxies are so dim, they're 1,000 times less luminous than our own Milky Way, yet they span similar distances. It's like comparing a candle to a spotlight. Both cast light, but one barely whispers its presence. The real shocker, these fossils shouldn't have survived this long. According to our current models of galaxy formation, such fragile, star-poor structures should have been torn apart by now, shredded by gravitational forces or absorbed by larger neighbors. Yet here they are, pristine, untouched, as if the universe forgot they existed. That's forcing scientists to rethink how galaxies evolve. Maybe dark matter played a bigger role in shaping the early cosmos than we thought, acting as a cosmic glue that held these fragile structures together against all odds. Studying them is like reading a diary from the universe's first chapters. Their pristine condition suggests they've been isolated for billions of years, untouched by the violent collisions and mergers that shaped most galaxies. That makes them perfect time capsules, offering clues about the conditions of the early universe. Some even contain stars so ancient they could be among the first ever born. If we could decode their secrets, we might finally understand how dark matter sculpted the cosmos, and why these ghostly relics managed to outlast everything else around them. The discovery raises tantalizing questions. Are there more of these fossils lurking in the darkness? Could they hold the key to unraveling dark matter's true nature? Every new detection peels back another layer of the mystery, proving that even in the vastness of space, the quietest whispers can carry the loudest revelations. These invisible galaxies aren't just oddities, they're cosmic puzzle pieces, waiting to show us how the universe really works. There's something haunting about the idea of a black hole drifting alone through the void, no star to orbit, no galaxy to call home, just an invisible predator silently carving its path through the cosmos. These aren't the supermassive beasts lurking at the centers of galaxies, but solitary wanderers, ejected from their birthplaces by violent cosmic events. Until recently, they were nearly impossible to detect, but thanks to a clever trick of physics called gravitational microlensing, astronomers are finally spotting these rogue black holes, and what they're finding challenges everything we thought we knew about how black holes form and move through the universe. Here's how microlensing works. When a massive object like a black hole passes between us and a distant star, its gravity bends the starlight like a lens, briefly magnifying the star's brightness. It's like watching a street lamp flicker as an unseen hand passes in front of it. By tracking these subtle flickers across the sky, researchers can piece together the black hole's mass, speed, and even its distance. And that's how they made the jaw-dropping realization some of these wanderers are far more common and far more massive than anyone predicted. One particularly startling discovery was a rogue black hole roughly 7 times the mass of our Sun, drifting through the Milky Way at over 100,000 miles per hour. But how did it get there? The leading theory is that it was flung into space during a catastrophic event, perhaps a supernova that went asymmetrically haywire, or a violent tango between multiple black holes in a dense star cluster. Whatever the cause, its existence suggests that the universe might be teeming with these dark nomads, lurking undetected in the spaces between stars. The implications are staggering. If rogue black holes are abundant, they could be stealthy architects of galactic evolution, subtly shaping the motion of stars and gas clouds as they pass through. Some might even carry the remnants of ancient, devoured stars in their gravitational grip, cosmic souvenirs from their violent pasts. And because they're invisible unless they're actively feeding, there could be thousands more out there, weaving invisible webs of gravity we've yet to map. But the biggest question remains, what happens when one of these wanderers gets too close? A rogue black hole passing through our solar system would be catastrophic, warping planetary orbits or even flinging worlds into the abyss. The odds are astronomically low, but the sheer possibility sends shivers down the spine. It's a reminder that space isn't just vast and beautiful, it's dynamic, unpredictable, and sometimes a little bit terrifying. Every new detection peels back another layer of the mystery. Are these black holes the orphans of galactic collisions, or the remnants of a wilder, more chaotic era in cosmic history? Each one tells a story, and as we learn to listen, we're discovering that the universe's darkest wanderers might hold some of its brightest secrets. The Milky Way should be surrounded by a swarm of tiny satellite galaxies, hundreds of them, if our best simulations are correct. Yet for decades, astronomers could only find a few dozen, leaving a glaring gap between prediction and reality. It's like expecting a bustling crowd and finding only a handful of stragglers. Where are all these missing galaxies? The answer might lie in one of the universe's greatest magic tricks, darkness. For years, scientists assumed most satellite galaxies would be bright enough to spot, packed with stars that glow against the cosmic backdrop. But what if they're not missing at all? What if they're simply too faint to see? Cutting-edge simulations now suggest these elusive dwarfs could be drowning in dark matter, their starlight smothered by the sheer weight of invisible mass. Picture a lantern shrouded in thick fog. The light's still there, but you'd never know unless you stood right next to it. That's the challenge astronomers face. The game changer has been ultra-sensitive telescopes and advanced computer models. These tools reveal that many satellite galaxies might be ultra-faint, with so few stars they blend into the Milky Way's glow. Some could contain just a few hundred stars scattered across thousands of light-years, making them virtually transparent against the night sky. Others might be dark galaxies, cosmic ghosts where dark matter outweighs visible matter by thousands to one, with barely any stars at all. Even stranger, these satellites might not orbit the Milky Way the way we thought. Instead of neat, predictable paths, they could be moving in chaotic streams, remnants of ancient collisions where larger galaxies tore them apart. Imagine tossing confetti into a whirlwind. Some pieces flutter close, others vanish into the distance. That's how these dwarfs might behave, their orbits stretched into faint, wispy trails that defy easy detection. The implications are profound. If these galaxies are out there but invisible, it means our census of the cosmos is wildly incomplete. Finding them could rewrite our understanding of galaxy formation, dark matter's role, and even the fate of our own Milky Way. Every new discovery peels back another layer, proving that sometimes the universe's biggest secrets aren't lost, just lurking in the shadows, waiting for the right light to reveal them. One of the most violent and mysterious events in the cosmos doesn't play by the rules. Fast Blue Optical Transients, or FBOT, are cosmic fireworks that blaze to life with unimaginable intensity, brighter than entire galaxies, only to vanish within days. Unlike supernova, which fade gradually over weeks or months, these explosions are here one moment and gone the next, leaving astronomers scrambling to catch them before they disappear. And their color, an eerie electric blue that defies all expectations. What makes FBOT so perplexing is how they defy classification. Some behave like supernova on steroids, while others seem to involve something even more exotic, like a star being torn apart by a hidden black hole or a newborn magnetar, a super-dense neutron star spinning at dizzying speeds. One of the most famous, nicknamed the Cow, erupted in a distant galaxy with such ferocity that it outshone its entire galactic neighborhood for a brief, dazzling moment. But instead of fading like a normal supernova, its light curve dropped off a cliff as if someone had flipped a cosmic switch. The leading theories are as wild as the events themselves. One suggests FBOT occur when a massive star collapses into a black hole, but instead of a clean explosion, it's more like a celestial train wreck. Material from the star's outer layers gets sucked into a swirling disk, then blasted outward in jets moving at nearly the speed of light. Another idea points to magnetars, whose intense magnetic fields could channel the explosion's energy into focused beams, creating that signature blue glow. Then there's the possibility of tidal disruption events, where a star wanders too close to a black hole and gets shredded like confetti, its debris glowing white-hot as it spirals into oblivion. But here's the kicker: FBOT might not even be one type of event. They could be a cosmic grab bag of catastrophes, each with its own trigger. Some leave behind no trace, while others, like the cow, linger as fading embers, hinting at a surviving compact object like a black hole or magnetar at their core. That's what makes them so maddening and thrilling to study. Just when researchers think they've pinned down a pattern, another FBOT flares up with twists nobody saw coming. The race is on to catch more of these ephemeral spectacles. With next-generation telescopes scanning the skies, astronomers hope to catch FBOT in the act, dissecting their light for clues about their origins. Every new detection peels back another layer of the mystery, proving that even in a universe full of explosive wonders, some of the most dazzling shows are the ones that vanish before we can fully understand them. Some planets are so light and airy, they shouldn't exist. Worlds so fluffy, they make Jupiter look like a heavyweight. Meet the cotton candy exoplanets, a bizarre class of giants with densities lower than anything in our solar system. These aren't just oddballs, they're cosmic contradictions floating through space like inflated balloons, their atmospheres stretching far beyond what physics says should be possible. Take WASP 107b, for example, a planet so puffy, if you could drop it in water, it would bob like a beach ball. What makes these planets defy logic? Normally, gas giants like Jupiter have thick, compressed atmospheres held together by immense gravity. But cotton candy planets break all the rules. WASP 107b orbits so close to its star that its atmosphere is literally boiling away. Yet it's still holding onto a gaseous envelope hundreds of times larger than Earth. It's like watching a dandelion stand firm in a hurricane. Somehow, against all odds, these planets cling to their vaporous shrouds without collapsing under their own feeble gravity. Scientists are scrambling to explain how they formed. One theory suggests these worlds started life much farther from their stars, where cooler temperatures allowed them to accumulate massive, lightweight atmospheres before migrating inward. Another idea points to extreme heat from their parent stars puffing up their outer layers like bread dough rising in an oven. But here's the real head-scratcher. Even with these explanations, some cotton candy planets are too big, too diffuse. Their cores, if they even have solid ones, must be improbably small to leave so much room for fluff. The implications are staggering. If these planets can exist, our models of planetary formation might be missing a key ingredient, perhaps a previously unknown process that lets gas accumulate without condensing into denser structures. Or maybe their atmospheres are laced with exotic molecules that behave differently under extreme heat. Every new observation adds to the puzzle, with some cotton candy planets showing signs of mysterious, high-altitude clouds that could hint at chemistry we've never seen before. These worlds aren't just curiosities, they're laboratories for testing the limits of physics. By studying how their atmospheres evaporate, interact with stellar winds, or even produce bizarre weather patterns, we're getting a front-row seat to processes that could rewrite planetary science. And with more ultra-puffy planets being discovered each year, one thing's clear: the universe has a flair for the dramatic, crafting worlds that challenge our imagination at every turn. So what's truly holding these cosmic cotton balls together? The answer might lie in the unseen hidden forces, unknown materials, or even entirely new physics waiting to be uncovered. Until then, these enigmatic planets will keep floating through space, quietly defying expectations and reminding us that when it comes to the cosmos, the rules are always up for debate. Hidden in plain sight around our planet, In fact, around every planet with a magnetic field, there's an invisible highway system made of superheated gas, twisting and turning through space like cosmic spaghetti. These are plasma tubes, vast structures of magnetized charged particles, some stretching tens of thousands of kilometers long. Until recently, we had no idea just how intricate or influential they really were. But new technology is pulling back the curtain, revealing a dynamic network that shapes everything from auroras to satellite disruptions. Plasma tubes form where Earth's magnetic field interacts with the solar wind, that constant stream of charged particles blasting from the sun. Picture the magnetic field as a shield, bending and warping under the solar wind's pressure like a flag rippling in a hurricane. Where these forces collide, they trap and funnel plasma into looping, tubular structures that snake around the planet. Some hover just a few hundred kilometers up, while others reach deep into space, connecting Earth to the Sun's own magnetic influence in ways we're only beginning to understand. What makes them so crucial? For starters, they're cosmic conductors, channeling energy that fuels space weather. When a solar storm hits, these tubes become superhighways for charged particles, funneling them toward the poles and igniting dazzling auroras. But they can also unleash chaos, overloading power grids, scrambling GPS signals, or even frying satellites. In 2012, a single plasma tube eruption knocked out radio communications across the Arctic for hours, proving just how powerful these hidden structures can be. Mapping them has been a nightmare. Traditional satellites couldn't detect their subtle magnetic fingerprints, and ground-based radar often mistook them for atmospheric noise. The breakthrough came with new sensors capable of measuring ultra-weak magnetic waves, combined with AI that pieces together faint patterns in the data. It's like listening for a whisper in a thunderstorm, but now we're finally hearing it. Recent findings suggest the tubes are far more numerous and complex than imagined, with some branching like tree roots or even merging into temporary junctions during solar storms. And Earth isn't special. Jupiter's plasma tubes are monstrous, stretching so far they could swallow our planet whole, while Mercury's tiny magnetic field still manages to weave delicate threads of plasma around its sun-scorched surface. Even Venus, lacking a global magnetic field, has ghostly versions formed by its interaction with the solar wind. Each system is a unique laboratory, showing how plasma behaves under different cosmic conditions. The big question now, can we predict their behavior? If we could forecast plasma tube activity like weather on Earth, we might protect satellites, stabilize power grids, and even safeguard astronauts from radiation surges. Some researchers are already testing models that use real-time solar data to simulate tube formation, a first step toward taming this invisible force. One day, we might even harness them, using their natural pathways to channel energy or propel spacecraft. For now, though, they remain a breathtaking reminder of how much we're still learning about the space around us. These plasma tubes aren't just curiosities, they're the veins of our solar system, pulsing with energy that connects every planet to the sun's fiery heartbeat. And as we map their twists and turns, we're not just solving a scientific puzzle, we're learning to navigate the invisible currents that shape our cosmic neighborhood. Tucked away in the cosmic microwave background, the afterglow of the Big Bang itself, there's a chilling anomaly that's been keeping scientists up at night. Known as the cold spot, this mysterious region of space is cooler than its surroundings by a fraction of a degree, a tiny difference that shouldn't exist according to standard cosmology. At first glance, it might seem insignificant, like a single puzzle piece slightly out of place, but this cold patch, spanning nearly 2 billion light-years, defies explanation, sparking wild theories ranging from cosmic defects to glimpses of another universe entirely. The cold spot first appeared in satellite data decades ago, dismissed initially as a statistical fluke, but as telescopes sharpened their gaze, the anomaly refused to vanish. It's not just cold, it's too cold, with a temperature drop that standard models can't account for. One leading explanation points to a supervoid, an enormous bubble of space with far fewer galaxies than average. The idea is that light passing through this void loses energy, like a marathon runner slowing down in thin mountain air, creating the illusion of a colder region. But here's the catch: the void needed to explain the cold spot would have to be so vast and empty, it challenges our understanding of how large-scale structures form. Then there's the twist. Some measurements suggest the void isn't big or empty enough to explain the temperature drop. That's where things get surreal. Alternative theories propose exotic physics at play: cosmic textures, defects in the fabric of space-time left over from the universe's fiery birth. Imagine the early cosmos as a pot of boiling water, with bubbles and cracks forming as it cools. If one of those cracks survived, it might manifest today as a cold spot, a fossilized wrinkle in reality itself, but the most mind-bending hypothesis: that the cold spot is a bruise from a collision with another universe. In certain multiverse theories, neighboring universes could nudge against ours, leaving behind imprints in the cosmic microwave background. It's like finding a handprint on a foggy window, evidence of something beyond the glass. Critics argue this is speculative, but supporters counter that the cold spot's properties align eerily well with simulations of such an encounter. The debate is far from settled. New surveys are scanning the cold spot with unprecedented precision, hunting for galaxies that might reveal the void's true nature or signs of exotic physics. Whatever the answer, this cosmic curiosity is more than a scientific puzzle. It's a beacon, reminding us that the universe still holds mysteries bold enough to rewrite the rules. Whether it's a void, a defect, or a doorway to another reality, the cold spot proves one thing: the cosmos always has one more surprise up its sleeve. Imagine a star being hurled across the galaxy like a cosmic slingshot, not just drifting through space, but rocketing at speed so fast it could cross the entire Milky Way in just a few million years. These aren't your average suns lazily orbiting the galactic core. They're hypervelocity stars blazing through the void at millions of miles per hour, flung outward by forces so violent they defy comprehension. And the culprit behind their interstellar exile, none other than the universe's ultimate bullies, supermassive black holes. For decades, these runaway stars were just theoretical oddities. Then came Gaia, the European Space Agency's star mapping powerhouse. By meticulously tracking the motions of billions of stars, Gaia spotted something astonishing: dozens of these hypervelocity fugitives, their trajectories tracing back like cosmic breadcrumbs to the hearts of distant galaxies. The math was undeniable. These stars weren't just drifting away, they'd been catapulted. The physics behind their expulsion is as brutal as it is elegant. Picture a binary star system, two suns locked in a graceful dance, drifting too close to a galaxy's central black hole. The black hole's gravity rips one star inward like a cosmic fishing hook, while the other gets flung outward at unimaginable speed. A galactic game of crack the whip, with the loser devoured and the survivor sent screaming into the abyss. That's not sci-fi, it's a phenomenon called the Hill's mechanism, and it's the only way we know to explain speeds like these. But Gaia's data revealed twists no one expected. Some hypervelocity stars aren't fleeing their home galaxies at all. They're intergalactic trespassers, hurled from distant galaxies millions of years ago and now streaking through our cosmic neighborhood. Others move too fast, their velocities hinting at black holes even more massive than we thought possible. And then there are the failed escapes, stars flung outward with just enough speed to reach the galaxy's edge before gravity eventually reels them back in like cosmic yo-yos. What makes these stars more than just celestial curiosities? They're forensic evidence revealing the hidden histories of the galaxies they fled. By studying their composition, scientists can decode the chemical makeup of their birthplaces, like tracing a bullet back to the gun that fired it. Their paths also map the gravitational landscape of the universe, exposing the invisible pull of dark matter and the locations of rogue black holes we'd never detect otherwise. Yet the biggest mystery remains: where are they all headed? Some might drift forever, destined to fade into the freezing void between galaxies. Others could one day slam into new galactic hosts, seeding them with foreign elements from their origins. And a rare few might even carry planets along for the ride, frozen, exiled worlds huddled around their speeding suns, racing toward destinations unknown. Hypervelocity stars are more than just cosmic speed demons. They're reminders that the universe is never still, never gentle. Forces beyond our imagination are constantly reshaping the heavens, turning quiet suns into intergalactic projectiles. And thanks to telescopes like Gaia, we're finally catching them in the act. Something isn't adding up in the cosmos, a discrepancy so glaring, it's tearing at the very fabric of modern astronomy. For years, scientists have relied on the Hubble constant, a critical number that tells us how fast the universe is expanding. But here's the problem: depending on how you measure it, you get wildly different answers. It's like checking two identical clocks and finding one ticking faster than the other, except these clocks are built into the fabric of reality itself. And now, with the James Webb Space Telescope peering deeper into the past than ever before, the mystery has only deepened, revealing galaxies in the early universe that behave as if dark energy, the force driving cosmic expansion, might not be what we thought at all. The Hubble tension, as scientists call it, boils down to two conflicting methods. One approach studies nearby supernova and pulsating stars, calculating an expansion rate of about 73 kilometers per second per megaparsec. The other method examines the cosmic microwave background, the afterglow of the Big Bang, and lands on a slower 67. That might not sound like much, but in the precise world of cosmology, it's a chasm. At first, astronomers assumed it was a measurement error, a cosmic typo we'd eventually correct, but the more data we collect, the wider the gap grows. Enter JWST, armed with infrared eyes sharp enough to spot ancient galaxies in unprecedented detail. What it's finding is even more baffling. Some of these early galaxies appear too massive, too evolved, as if the universe hit the fast-forward button on star formation. If dark energy, the mysterious force thought to accelerate expansion, has been constant over time, these galaxies shouldn't exist in their current state. Their very presence hints that dark energy's influence might have fluctuated, growing stronger or weaker at different epochs. It's as if we've been reading the universe's diary and just stumbled upon a chapter we didn't know was missing. One radical theory suggests dark energy isn't a static force but an evolving one, changing strength as the cosmos ages. Another posits that our understanding of gravity itself is incomplete, that Einstein's equations, the bedrock of modern physics, might need rewriting on cosmic scales. Then there's the possibility of undiscovered particles or fields, lurking in the background and tweaking the universe's expansion rate like invisible hands on a dial. But the most unsettling idea, that we're seeing evidence of a crisis in cosmology, a fundamental flaw in how we model the universe. JWST observations of these two mature early galaxies could mean our cosmic timeline is off, or that dark energy's behavior is far weirder than we imagined. Every new dataset tightens the knot, leaving astronomers with more questions than answers. What's at stake isn't just a number, it's our entire understanding of cosmic history. If dark energy isn't constant, the fate of the universe changes. Maybe expansion won't continue accelerating indefinitely. Maybe it will slow, reverse, or even rip spacetime apart. The Hubble tension isn't just a puzzle, it's a doorway, and JWST is giving us our first real glimpse of what might lie on the other side. One thing's certain, the cosmos is playing a game with rules we're only beginning to decipher, and we're just starting to realize how little we truly know. The sun isn't just pouring light onto Earth, it's raining down ghostly particles called neutrinos, trillions of which pass through your body every second without you ever noticing. For decades, these elusive particles puzzled scientists because they seemed to vanish on their way from the sun's core to our detectors. But the mystery wasn't a glitch, it was a cosmic dance. Neutrinos, it turns out, have a habit of shape-shifting mid-flight, flipping between three different flavors like a magician's endless card trick. This bizarre behavior, once written off as impossible, is now rewriting our understanding of both the sun's furnace and the fundamental rules of particle physics. The breakthrough came when ultra-sensitive experiments like the Sudbury Neutrino Observatory and Japan's Super Kamiok and caught neutrinos red-handed in the act of transformation. Imagine setting up a camera to photograph a chameleon, only to discover it doesn't just change color, it morphs into entirely different animals. That's what scientists witnessed. Electron neutrinos born in the sun's nuclear fires were arriving on Earth as muon or tau neutrinos, proving these particles had mass, something the standard model of physics swore couldn't happen. The implications were seismic. If neutrinos could oscillate, their mass, however tiny, meant our rulebook for the universe was missing pages. But the real shocker was what this revealed about the sun itself. Neutrinos are the only direct evidence of the fusion reactions powering our star, and their flavor switching meant earlier detectors had been undercounting them by 2/3. It's like trying to measure a waterfall by catching only every third drop. By decoding these oscillations, researchers could finally confirm the sun's core temperature, its energy output, even the mind-bending quantum mechanics governing how particles behave under extreme pressure. Suddenly, we weren't just observing the sun, we were peering into its nuclear heart with unprecedented clarity. Yet the story gets stranger. Neutrinos don't just oscillate, they do it differently depending on their energy. Some high-energy neutrinos switch flavors more lazily, while low-energy ones flicker like candle flames in a breeze. This energy-dependent dance hints at forces beyond the standard model, possibly tied to undiscovered particles or hidden dimensions. Some theories even suggest sterile neutrinos, phantom particles that interact only via gravity, could be pulling strings behind the scenes. What does this mean for the cosmos? Neutrinos are everywhere, forged in stars, supernova, even the Big Bang itself. If they're hiding secrets about mass, gravity, or unknown physics, unlocking their rhythms could illuminate everything from dark matter to why the universe is made of matter at all. Every new experiment, from ice-bound detectors in Antarctica to liquid argon chambers deep underground, brings us closer to deciphering their code. The sun's dancing neutrinos aren't just a curiosity, they're whispers from the quantum shadows, reminding us that even the smallest particles hold the keys to the universe's biggest mysteries. Gamma-ray bursts are supposed to follow a script: a blinding flash of high-energy radiation followed by a lingering afterglow visible in X-rays, optical light, and radio waves. But some bursts break all the rules, vanishing without a trace the moment their initial flash fades. These are the dark gamma-ray bursts, cosmic explosions so mysterious they leave astronomers staring at empty sky where brilliant fireworks should be. The first clues came from satellites like Swift and Fermi, which detect gamma-ray bursts across the universe. Normally, these missions pinpoint a burst's location, then swing telescopes around to catch the aftermath. But with dark bursts, the follow-up observations revealed nothing. No fading glow, no heat signature, just an eerie silence where there should have been echoes. At first, scientists assumed the afterglows were simply too faint, buried in the noise of distant space. But as more of these phantom bursts piled up, a terrifying realization set in: something was fundamentally different about these explosions. One leading theory points to the environment around these bursts. Imagine a star dying in the densest neighborhood of its galaxy, surrounded by thick clouds of gas and dust. When it explodes, the initial gamma rays punch through, but the afterglow, created when shockwaves plow into surrounding material, gets smothered before it can escape. It's like setting off a flare inside a bank vault. The light might never reach the outside world. Some dark bursts could even occur in regions packed with dark matter, whose gravitational pull might warp or trap the afterglow entirely. Then there's the wildcard possibility, exotic physics. What if these bursts aren't just hidden but fundamentally different? Some models suggest dark bursts could be the work of cosmic strings, hypothetical defects in spacetime left over from the Big Bang. If one of these ultra-dense filaments snapped, it might release a gamma-ray burst without the usual debris field needed for an afterglow. Others speculate about quark nova events, where a neutron star doesn't just collapse into a black hole but transforms into a soup of free-floating quarks, producing a burst with unique signatures. The real frustration is how little we can learn from these ghosts. Without an afterglow, astronomers can't measure the burst's distance, its host galaxy, or even confirm whether it came from a collapsing star or emerging black hole. It's like hearing a scream in the dark but never finding the source. New telescopes are trying to crack the mystery, scanning dark bursts in infrared or hunting for neutrinos that might slip through where light gets trapped. Every detection is a victory, but the more we find, the clearer it becomes some of the universe's most violent events might be hiding in plain sight, their secrets locked away by physics we're only beginning to imagine. The Tarantula Nebula has always been a spectacle, a swirling cosmic cloud where stars are born at a frenzied pace, glowing so brightly it's visible even from neighboring galaxies. But when the James Webb Space Telescope turned its infrared gaze toward this stellar factory, it revealed something no one expected: hidden pockets of star formation, completely invisible to earlier telescopes. These aren't just dim or distant nurseries, they are dark, star-forming regions, cloaked in so much dust that traditional observatories missed them entirely. Now, scientists are scrambling to understand how these stealthy cradles of new stars could exist, let alone thrive, in conditions once thought impossible for stellar birth. For decades, astronomers assumed the tarantula's most active star-forming sites were its bright, gaseous tendrils, where young stars light up their surroundings like cosmic lanterns. But JWST piercing infrared vision exposed a parallel universe of creation, thick, cold cocoons of gas and dust so dense they block nearly all visible light. Inside these shadowy pockets, protostars are taking shape, their faint heat signatures detectable only because JWST can peer through the obscuring veil. It's like discovering an entire hidden city beneath a metropolis you thought you knew. The implications are staggering. These dark stellar nurseries defy conventional models of star formation, which suggest that intense radiation from nearby massive stars should prevent gas from collapsing into new suns. Yet here they are, bundles of gas somehow resisting the onslaught, collapsing in quiet defiance. Some theories suggest magnetic fields might be shielding these regions, acting like cosmic force fields. Others propose turbulence within the nebula creates temporary safe zones, like calm eddies in a raging river. Whatever the mechanism, their existence means our understanding of star birth is far from complete. Even more puzzling is the composition of these hidden nurseries. JWST spectrographs detected molecules like water ice and complex hydrocarbons in the dust, ingredients not just for stars but for planets. That raises a tantalizing question. Could these dark regions be incubating planetary systems alongside their fledgling stars? If so, they might be churning out worlds under conditions we've never studied, with chemistry skewed by the nebula's harsh environment. The tarantula's secret factories aren't just rewriting astrophysics textbooks, they're forcing us to reconsider where life might arise in the universe. If stars can form in such hostile, obscured environments, then similar nurseries could be lurking in other extreme cosmic locales, hidden from view but teeming with activity. JWST discovery isn't just a glimpse behind the curtain. It's proof that even in the brightest corners of the cosmos, the darkest places hold the most surprising secrets. Jupiter isn't just a giant ball of gas, it's a cosmic orchestra, broadcasting eerie melodies across space that no human ear could ever hear. When NASA Juno spacecraft slipped into orbit around the solar system's largest planet, its instruments picked up something unexpected: haunting waves of electromagnetic energy rippling through Jupiter's magnetosphere, transforming the void into a symphony of crackles, whistles, and hums. Scientists call them chorus waves, and their discovery revealed that Jupiter doesn't just dominate its corner of the solar system it sings. These aren't sound waves in the traditional sense. In the vacuum of space, where molecules are too sparse to carry vibrations, Jupiter's music is carried by charged particles dancing along magnetic field lines. Picture Earth's northern lights, but instead of silent curtains of color, imagine each flicker producing a tone, a chorus of millions of charged electrons spiraling through Jupiter's monstrous magnetic field, emitting radio frequencies as they go. The result, a soundscape that, when shifted into audible range, resembles everything from sci-fi laser blasts to a chorus of chirping birds. What makes these emissions so extraordinary is their source. Jupiter's magnetosphere is the largest structure in the solar system, so vast that if it glowed visibly, it would appear 2 to 3 times bigger than the full moon in Earth's sky. This titanic magnetic field acts like a particle accelerator, whipping electrons to near light speeds. As these particles ricochet between the planet's poles, they generate waves that cascade through space, some lasting mere milliseconds, others persisting for minutes. The most intense waves originate near Jupiter's volcanic moon Io, where eruptions spew sulfur dioxide into space, ionizing into a plasma torus that fuels the planet's electromagnetic concert. But the real shock came when researchers realized these waves aren't just background noise, they're reshaping Jupiter's space environment. Some chorus waves act like particle pumps, funneling energetic electrons into the planet's atmosphere and sparking auroras brighter than any on Earth. Others scatter particles into radiation belts so intense they've challenged Juno's radiation-hardened electronics. It's a delicate balance. The same forces creating this cosmic music also generate lethal radiation zones that could fry spacecraft in minutes. The parallels to Earth's own magnetosphere are striking. Our planet produces similar chorus waves, though far weaker, like comparing a whisper to a thunderclap. Studying Jupiter's extreme versions helps scientists unravel how magnetic fields protect planets, accelerate particles, and even influence atmospheric chemistry. Some researchers speculate that exoplanets with similarly intense magnetospheres might broadcast their own chorus waves, detectable by future telescopes. Imagine tuning into alien worlds not by their light but by their magnetic melodies. Juno's recordings have become more than data. They're a window into the invisible forces sculpting our solar system. Listen closely and you'll hear the voice of a planet that refuses to be silent, its magnetic field humming with the energy of 1 trillion thunderstorms. In Jupiter's chorus, we're not just hearing strange sounds, we're eavesdropping on the hidden rhythms of the cosmos itself. For billions of years, the universe has been spinning an invisible web, one so vast it makes entire galaxies look like mere dewdrops clinging to its strands. Until recently, this cosmic web existed only in theory, a ghostly network of dark matter and superheated gas hypothesized to link galaxies across unfathomable distances. But now, for the first time, astronomers have caught glimpses of its shimmering filaments directly, revealing a scaffolding so immense it dictates the very architecture of existence. These aren't just faint wisps between galaxies. The cosmic web's filaments are highways of matter and energy, some stretching hundreds of millions of light years across the void. Picture the universe as a bustling metropolis. Galaxies cluster like cities at the intersections of these filaments, while the strands themselves act as cosmic supply routes, funneling gas into galactic hubs where it ignites into new stars. For decades, we could only infer their presence by mapping the distribution of galaxies or studying distortions in the light of distant quasars. like tracing the outline of a spiderweb by watching how dust settles around it. But new techniques have finally pulled these structures into focus, exposing a hidden skeleton beneath the skin of the cosmos. The breakthrough came from combining gravitational lensing with X-ray observations. When light from distant galaxies passes near these filaments, it bends subtly, betraying the gravitational tug of their dark matter. Meanwhile, space telescopes like Europe's Newton detected the faint glow of million-degree gas clinging to those same filaments, like steam rising from warm pavement. One of the most stunning images yet captures a filament bridging the Able 279 galaxy cluster, a river of hot plasma and dark matter so massive it could funnel the mass of 10,000 Milky Ways. What's truly mind-bending is how these filaments shape cosmic evolution. Without them, galaxies would float adrift like ships without currents, never clustering into the superclusters we see today. They're also cosmic recycling plants. When galaxies collide or explode, the filaments catch ejected gas and dust, eventually channeling it back into new generations of stars. Some researchers even suspect these strands act like particle accelerators, speeding cosmic rays to energies we can't reproduce on Earth. Yet the greatest mystery remains what fuels them. The web's filaments shouldn't stay hot enough to glow in X-rays unless some unknown energy source constantly reheats them. One theory points to shockwaves from colliding galaxy clusters, while others suggest dark matter particles might annihilate within the strands, releasing bursts of heat. There's even speculation that primordial black holes, relics from the Big Bang, could lurk within these filaments, their gravity stirring the gas like spoons in a boiling pot. As we map more of this hidden architecture, we're realizing the cosmic web isn't just backdrop, it's the universe's circulatory system, its nervous system, its blueprint all in one. Every galaxy we see, every star we admire, exists because these filaments whispered to the cosmos, telling matter where to gather and how to grow. And now at last we're learning to read their language. The Moon's surface is a graveyard of ancient impacts, vast lava plains, and eerie patterns that have puzzled astronomers for centuries. Among its most striking mysteries are the lunar swirls, delicate, bright tendrils curling across the landscape like cosmic brushstrokes. The most famous, Rheanur Gamma, spans nearly 40 miles, its gleaming arc standing in stark contrast to the dark volcanic plains around it. For decades, these formations defied explanation, dismissed as mere quirks of lunar geology. But new research is revealing they might be the fingerprints of forces far stranger than anyone imagined. Early theories suggested the swirls were leftovers from comet impacts, with icy debris scattering across the surface and brightening the regolith. Others proposed they were scars from meteorite strikes, their shockwaves altering the soil's reflectivity, but the truth turned out to be far more intriguing. When lunar orbiters mapped the swirl's magnetic fields, they found something startling. These patterns overlap with patches of localized magnetism, as if invisible shields were protecting the bright soil from the relentless darkening effects of solar radiation. It's like finding a handful of snow-white stones in a sun-bleached desert. Some force is keeping them pristine while everything around them weathers away. The leading theory now points to a cosmic dance between lava and magnetism. Billions of years ago, when the Moon was volcanically active, molten rock rich in iron may have bubbled up to the surface. As it cooled in the presence of an ancient magnetic field possibly generated by a long-dead lunar dynamo, it froze traces of that magnetism into the rock. Over time, these magnetic bubbles acted like umbrellas, deflecting the solar wind's charged particles and preventing the soil beneath from darkening. The result, those luminous swirls we see today, their brilliance preserved by magnetic ghosts of the Moon's fiery past, but the plot thickens. Some swirls don't align neatly with known magnetic anomalies, and their shapes are too intricate to be explained by simple lava flows. That's where wilder ideas come in. One hypothesis suggests the swirls were sculpted by mini-magnetospheres, bubble-like magnetic fields generated as solar wind particles interacted with the lunar surface. Another proposes that electrostatic forces kicked up by micrometeorite impacts levitated fine dust into these intricate patterns. And then there's the tantalizing possibility that the swirls mark the graves of extinct lunar volcanoes, their last gasps of gas creating transient magnetic fields that left these eerie imprints behind. The implications stretch beyond the Moon. If magnetic anomalies can preserve surface features for eons, similar swirls might exist on Mercury, asteroids, or even Mars, hidden records of ancient magnetic activity waiting to be discovered. Unlocking their secrets could rewrite our understanding of how airless worlds evolve under the relentless bombardment of space weather. Every new lunar mission brings us closer to solving the riddle. With instruments capable of measuring nanoscale magnetism and mineral composition, scientists are piecing together a story written in iron and sunlight. These swirls aren't just curiosities, they're time capsules holding clues to the Moon's turbulent youth and the invisible forces that shaped its face. And as we decode their message, we're reminded that even our closest celestial neighbor still has secrets to share whispered in the language of magnetism and light. Betelgeuse, the ruby-red shoulder of Orion, has always been a star of drama. But in late 2019, it took center stage in a cosmic mystery that had astronomers holding their breath. Over just a few months, this colossal supergiant dimmed by nearly 2/3, its usual brilliant glow fading to a faint ember. Panic rippled through the astronomy community. Was this the prelude to a supernova, a stellar explosion so bright it could outshine the Moon? Telescopes around the world swiveled toward Orion, hoping to witness a once-in-a-millennium event. Then, just as suddenly as it dimmed, Betelgeuse roared back to life, leaving everyone wondering what just happened. The truth turned out to be stranger than fiction. High-resolution images from the Hubble Space Telescope revealed the culprit, a monstrous cloud of stardust ejected from Betelgeuse itself. This wasn't just any dust, it was a cosmic sneeze, a plume of superheated material so vast it briefly blocked the star's light from our perspective. Betelgeuse, it seems, is in a volatile phase of its life, shedding material in fits and starts as it burns through its final reserves of fuel. Imagine a candle sputtering, wax bubbling and spitting as the flame flickers, except this candle is 1,000 times larger than our Sun. But here's the twist. While the dimming event wasn't a supernova warning sign, it did offer a rare glimpse into how stars like Betelgeuse behave in their death throes. Spectroscopic data showed the star's surface heaving with turbulent waves, its outer layers churning like a boiling cauldron. This isn't the calm before the storm, it's the storm itself, a slow-motion unraveling that could last centuries. Some models now suggest Betelgeuse's dimming might have been caused by a colossal convection cell, a bubble of hot plasma rising from its depths and cooling as it reached the surface, temporarily shading part of the star. The million-dollar question remains, when will Betelgeuse go supernova? The answer is frustratingly uncertain. It could be tomorrow, or it could be 100,000 years from now. What we do know is that the star's core is fusing elements at a breakneck pace, building up layers of silicon, oxygen, and eventually iron, the ticking time bomb that will trigger its collapse. When that happens, the explosion will be visible even in daylight, a celestial spectacle unmatched in human history. Until then, Betelgeuse is giving us a front-row seat to the messy, unpredictable process of stellar demise. And the drama isn't over. Recent observations suggest Betelgeuse's brightness is still fluctuating unpredictably, as if the star can't quite settle down. Some researchers speculate it might be preparing for another great dimming, while others think we're seeing the early stages of a deeper transformation. One thing's certain, Betelgeuse isn't just a star. It's a cosmic performance, and we're lucky enough to be watching Act 1. Whether it bows out with a bang next week or millennia from now, its final act will be the show of the universe. When 2I/Borisov streaked across our skies in 2019, It wasn't just another comet, it was a cosmic postcard, the second known visitor from another star system after Oumuamua. But unlike its enigmatic predecessor, which left scientists scratching their heads, Borisov arrived with a spectacle. Its brilliant tail, glowing with expelled gas and dust, offered humanity its first real chance to study the chemistry of a world born around another sun. As telescopes worldwide trained their lenses on this interstellar traveler, they uncovered secrets that challenged our assumptions about how planetary systems form and what ingredients might be universal across the galaxy. The first shock came from Borisov's composition. Most comets in our solar system carry signatures of water, carbon dioxide, and carbon monoxide, frozen relics from the protoplanetary disk that birthed them. But Borisov was different. When the Atacama Large Millimeter Array analyzed its outgassing, it detected staggering amounts of carbon monoxide, nearly 26 times more than the average solar system comet. This wasn't just a minor variation, it was a screaming clue about the comet's origins. Carbon monoxide freezes solid only in the coldest reaches of a planetary system, meaning Borisov likely formed in the frigid outskirts of its home star, far beyond where water could stay icy. Then came the real curveball, cyanogen gas. This toxic compound, famous for its role in science fiction as a death cloud, poured from Borisov's nucleus at concentrations that would make our local comets seem tame. On Earth, cyanogen forms in industrial processes or deep space molecular clouds, not typically in comets. Its presence hinted at extreme conditions in Borisov's birthplace, perhaps a young system roiled by intense radiation or violent collisions that forged exotic chemistry. Some researchers even speculated the comet could have been flung from a carbon-rich red giant star, where such molecules thrive in the chaotic stellar winds. But the most tantalizing discovery was yet to come. As Borisov neared its closest approach to the Sun, the Hubble Space Telescope spotted something unprecedented. The comet was crumbling. Unlike solar system comets, which often survive their trips around the Sun, Borisov began fracturing into fragments, its nucleus splitting like a cracked egg. This wasn't just a case of solar heating. The comet's very structure seemed fragile, as if its birthplace lacked the gravitational kneading that toughens comets in our system. The implications were profound. Maybe other planetary systems don't pack their comets as densely as ours, leaving them more vulnerable to disintegration. By the time Borisov faded into the depths of space, it had rewritten the textbook on interstellar objects. Its chemistry suggested planetary systems could be far more diverse than we imagined, with some crafting comets richer in deadly gases and others lacking the sturdy architecture we take for granted. Every speck of dust it left behind carried a message. The universe isn't just vast, it's wildly inventive, cooking up celestial bodies under rules we're only beginning to decode. What does this mean for the next interstellar visitor? If Borisov is any indication, we might need to rethink everything from how we model alien solar systems to what hitchhiking compounds could one day drift between stars. One thing's certain, the cosmos doesn't play by our expectations, and every rogue traveler like Borisov brings a fresh challenge and a chance to glimpse the unseen recipes of creation. Astronomers have long thought black holes came in two sizes small: stellar mass remnants of collapsed stars and gargantuan supermassive beasts anchoring galaxy centers. But in 2020, the Hubble Space Telescope found something that shattered that binary. A black hole roughly 50,000 times the mass of our Sun, lurking in the outskirts of a nearby galaxy called NGC 2730. This wasn't just an oddity, it was an impossibility. According to every model of black hole formation, mid-sized monsters like this shouldn't exist, yet here one was, staring back at us from cosmic next door. The discovery sent shockwaves through astrophysics. Dubbed Goldilocks for being neither too big nor too small, this black hole defies all expectations about how such objects grow. Stellar mass black holes form when massive stars collapse, while supermassive ones likely start as seeds in the early universe, feasting on gas and mergers to balloon to billions of solar masses. But mid-sized black holes, they're the universe's missing link, too hefty to form from a single star's death, yet too puny to fit supermassive formation theories. Spotting one in a relatively quiet galaxy like NGC 2730 makes it even more baffling. It's like finding a skyscraper in the middle of a rural village with no construction crew in sight. Hubble pinpointed the object by watching the frenzied dance of stars near the galaxy's edge, their orbits betraying the gravitational grip of something unseen. The speed and path of these stars revealed a mass 50,000 suns strong, crammed into a space smaller than our solar system, a textbook black hole signature, but with a mass no textbook expected here. Some researchers initially dismissed it as a cluster of smaller black holes, but follow-up observations ruled that out. The star's movements required a single, dense object, something far more exotic. The leading theory for Goldilocks' existence, a cosmic glutton that got lucky. One possibility is that it formed in the wreckage of a dwarf galaxy, one so small it was gobbled up long ago by NGC 2730, its central black hole left behind like a fossil. Another idea suggests it grew via a chain reaction of stellar collisions in a packed star cluster, where black holes merge over and over like snowballs rolling downhill. But neither explanation fully fits. The dwarf galaxy scenario requires an unlikely series of mergers, while the collision model struggles to reach 50,000 solar masses without the black hole getting kicked out by gravitational recoil. Even more perplexing is what this means for black hole evolution. If mid-sized black holes are hiding in plain sight, they could be the universe's missing stepping stones, the middle stage between stellar and supermassive varieties. That would rewrite our understanding of how galactic titans like Sagittarius at the Milky Way's center got so big. Maybe they didn't start as seeds in the early universe but grew from mergers of these impossible intermediates. Or perhaps Goldilocks is a fluke, a statistical outlier in a cosmos that still prefers its black holes extra small or extra large. Future telescopes like the upcoming Nancy Grace Roman Space Telescope aim to hunt more of these misfits. Every new detection could tilt the scales toward one theory or another, revealing whether Goldilocks is a cosmic rarity or proof we've been blind to an entire class of black holes lurking in the shadows. For now, it stands as a humbling reminder that the universe doesn't care about our neat categories. Somewhere between the stellar corpses and the galactic giants, there's a wild frontier of black holes waiting to be discovered, and their very existence challenges everything we thought we knew about how darkness takes shape in the cosmos. Dark matter refuses to play by the rules. It doesn't interact with light, barely acknowledges regular matter, and yet dictates the fate of galaxies with its invisible grip. Now scientists are chasing an even wilder idea. What if this elusive substance isn't just hanging idly in space, but churning in massive, swirling vortices that twist galaxies into their peculiar shapes? The whirlpool dark matter hypothesis suggests these hidden currents could be the missing piece in one of astronomy's longest-standing puzzles: why some galaxies rotate faster than their visible matter should allow. Picture a cosmic whirlpool, an invisible maelstrom spinning beneath the surface of a galaxy. While stars and gas trace orderly orbits, this dark matter vortex tugs at them from below, accelerating their motion like a hidden hand stirring a cup of coffee. The concept flips traditional thinking on its head. Instead of dark matter being a static halo around galaxies, it could be dynamic, even turbulent, with currents and eddies sculpting the cosmos in ways we've never imagined. The idea gained traction when astronomers noticed odd twists in galaxy rotation curves, speed measurements that didn't align with smooth, predictable distributions of mass. Some galaxies spin as if their outer stars are being whipped along by something unseen, something moving. The math is mesmerizing. if dark matter swirls, its motion would generate subtle gravitational shifts, warping space-time like underwater currents bending light. These vortices wouldn't just tweak rotation speeds, they could explain bizarre galactic structures, like warped disks or spiral arms that seem to ripple outward against the pull of gravity. One study even simulated how such vortices might form, suggesting they're born from cosmic collisions, where clusters of dark matter slam together and slosh like water in a shaken bucket, leaving behind persistent swirls. But proving it is another challenge. Dark matter's trademark is its silence, no light, no easy signals to track. Researchers are hunting for indirect fingerprints, like stars that seem to bob in place as they orbit, their path slightly kinked by passing dark matter waves. Others are scouring galaxy clusters for telltale distortions in gravitational lensing patterns, where light bends around invisible whirlpools like river currents around rocks. The most tantalizing hints come from dwarf galaxies, which orbit larger galaxies like flies trapped in a spider's web. Their erratic movements might not be random chaos, but the result of swimming through these unseen vortex fields. Skeptics argue the theory overcomplicates things. Why invent turbulent dark matter when simpler models mostly work? Yet the universe has a habit of favoring the bizarre over the bland. If these vortices exist, they'd rewrite not just galaxy dynamics but the entire story of cosmic structure formation. Maybe dark matter isn't the universe's silent scaffold but an active participant, its hidden currents shaping galaxies like wind-shaped dunes. Every new telescope, every deeper simulation brings us closer to testing this radical vision. Whether it holds up or collapses under scrutiny, one thing's clear: the enigma of dark matter just got a lot more interesting. If we're right, the cosmos isn't just filled with invisible mass, it's alive with motion, a dance of shadows we're only beginning to see. Galaxies aren't supposed to come back from the dead. Once their star-forming gas runs dry, they're expected to fade into quiet retirement, their remaining stars burning out over eons like embers in a dying fire. But deep in the constellation Cetus, astronomers have found a cosmic zombie, a galaxy designated Joan 4038137 that somehow roared back to life after billions of years of silence. This celestial Lazarus, dormant for nearly half the age of the universe, is now birthing new stars at a furious pace, defying every rule we thought governed galactic evolution. At first glance, Joan 4038137 looked like any other red and dead galaxy, its color betraying an aging population of stars, its spiral arms devoid of the blue glow of youthful stellar nurseries. Then, observations from the Atacama Large Millimeter Array revealed the impossible: vast reservoirs of cold hydrogen gas, the raw material for star formation, swirling where none should exist. Even more shocking was the infrared signature patches of intense heat, evidence of newborn stars igniting across the galaxy like fireworks in slow motion. It was as if a ghost town had suddenly sprouted skyscrapers overnight. Theories about this reanimation range from the dramatic to the downright bizarre. One leading idea suggests the galaxy survived a near-fatal collision, grazing another galaxy just enough to siphon off fresh gas without fully merging. Imagine a drought-stricken tree, its roots accidentally tapping into a hidden aquifer after a landslide shifts the terrain. Another possibility involves a dormant black hole at the galaxy's center suddenly reactivating, its jets pumping energy into the surrounding gas and jump-starting star formation. But the most tantalizing explanation: dark matter. Simulations show certain configurations of dark matter halos could channel intergalactic gas into dead galaxies like a cosmic Roman IV drip, reviving them long after their natural star-forming fuel was spent. What makes this resurrection so unsettling is its timing. The universe's star-forming heyday peaked around 10 billion years ago, with most galaxies slowing their birth rates as intergalactic gas grew scarce. For one to reignite now against the cosmic tide implies forces at work we've never accounted for. It's like finding a frozen mammoth suddenly thawing and grazing again. Nature isn't supposed to work backward. Yet here we are, staring at a galaxy that's somehow cheating time. The implications ripple far beyond this one anomaly. If dead galaxies can reboot, our entire understanding of galactic life cycles needs rewriting. Census counts of inactive galaxies might be missing stealthy revivals, their rekindled starlight too faint to detect. And if dark matter or black holes are the culprits, then the universe could be teeming with sleeper galaxies waiting for the right trigger to explode back into life. For now, Joan 4038137 stands as a cosmic question mark. Is it a fluke or the first of many undead galaxies we'll uncover? Every new telescope trained on it peels back another layer, but the galaxy isn't giving up its secrets easily. One thing's certain, the universe has a penchant for second acts, and this once-dead galaxy is delivering a performance nobody saw coming. Most planets enjoy a single sun, basking in its steady light as they trace predictable orbits. But deep in the constellation Cygnus, astronomers found a world that laughs in the face of celestial simplicity. A planet dancing not with one star, not two, but three blazing suns. Known as KY5b, this real-life Tatooine doesn't just exist in a triple-star system. It somehow survives a gravitational circus that should have torn it apart long ago. At first glance, KY5b seems impossible. Nestled within a system where three stars whirl around each other in a complex ballet, the planet orbits the primary star while the other two suns, locked in their own tight binary dance, swing around the pair at a dizzying distance. The gravitational forces at play here are mind-bending. Picture a roller coaster where the track itself is wobbling, the safety rails are alive, and the cart occasionally gets yanked sideways by invisible hands. That's the daily reality for this planet, yet against all odds, it's held its orbit for billions of years. The secret to its survival, sheer cosmic luck. Computer simulations reveal KY5b likely formed in a quieter era, when the three stars were farther apart, allowing the planet to coalesce in a relatively stable orbit. As the stars gradually tightened their dance, their gravity should have flung the planet into space or devoured it whole. Instead, KY5b found a fragile equilibrium, a sweet spot where the tugs from its three suns nearly cancel each other out. It's the astronomical equivalent of balancing a pencil on your fingertip during an earthquake, miraculous, precarious, and utterly fascinating. But the real spectacle is the sky view from KY5b's surface, if it has one. On a day when all three suns are aligned, the planet might experience a fleeting moment of single-star warmth before another sun rises, casting multiple shadows that stretch and warp as the stars shift positions. During triple sunsets, the horizon could blaze with overlapping hues as the stars, each a different size and color, dip below the horizon in staggered succession. And then there are the eclipses, where one star crosses another, creating a celestial light show no single star system could ever match. Astronomers are obsessed with KY5b not just for its novelty, but for what it reveals about planetary resilience. If a world can endure this gravitational gauntlet, it suggests planets might thrive in even the most chaotic corners of the galaxy. Perhaps even in quadruple star systems we've yet to discover. Every new observation peels back another layer of the mystery, proving that when it comes to cosmic real estate, the universe has a flair for drama we're only beginning to appreciate. Yet the question lingers, how many more KY5b's are out there? With triple star systems making up nearly 10% of all stellar configurations, the discovery hints at a hidden population of planets clinging to survival in gravitational war zones. Each one would rewrite the rules of planetary formation, forcing us to reconsider where and how life might find a foothold in the cosmos. For now, KY5b stands as a defiant oddity, a world that refuses to play by the rules, reminding us that the universe's imagination far outstrips our own. The Milky Way isn't just a majestic spiral of stars, it's a cosmic crime scene, littered with the remnants of galaxies it devoured over billions of years. Thanks to the Gaia Space Telescope, we're now seeing the evidence in stunning detail. Ghostly rivers of stars stretched and splattered across the galactic halo like paint flung from a brush. These aren't random scatterings, they're the shredded remains of dwarf galaxies, swallowed whole and digested into swirling trails that trace the Milky Way's violent history. One of the most striking examples is the Sagittarius Stream, a glittering arc of stars torn from a dwarf galaxy now in its death throes. Gaia's precise measurements revealed this structure isn't just a single ribbon, it's a tangle of multiple wraps coiled around our galaxy like a cosmic serpent. Each loop corresponds to a different orbital pass, marking moments when the dwarf galaxy swung too close and paid the price. The stars in these streams carry chemical fingerprints distinct from the Milky Way's native population, richer in heavy elements forged in smaller, hotter stellar nurseries. It's forensic astronomy, with each photon telling a story of galactic cannibalism. But Sagittarius is just the tip of the iceberg. Fainter, older streams crisscross the halo, some so diffuse they're barely detectable. One, dubbed the Phoenix Stream, appears to be the last gasp of a galaxy so ancient, its stars formed before the Milky Way finished growing. Unlike the metal-rich Sagittarius debris, Phoenix's stars are primitive, nearly pure hydrogen and helium, relics of a time before supernova polluted the cosmos with heavier elements. Finding them was like stumbling upon a prehistoric cave painting hidden beneath layers of modern graffiti. The real shock came when Gaia mapped the Helmy Stream, a group of stars moving in the opposite direction to most Milky Way material. These rebels aren't just passing through, they're the leftovers of a dwarf galaxy that struck our own at a steep angle, its orbit preserved like a fossil in the stellar record. Computer simulations suggest this collision happened 8 to 11 billion years ago, making it one of the Milky Way's earliest meals. The fact that these stars still cling together after so long hints at dark matter's role. Perhaps their original galaxy's dark halo acted as a gravitational glue, slowing their assimilation. What's emerging is a picture of the Milky Way as a relentless predator, growing not just by accreting gas but by feasting on smaller galaxies. Some streams even intersect, hinting at chaotic moments when multiple dwarfs were torn apart simultaneously. One such knot near the constellation Sextans may mark the site of a galactic feeding frenzy, where several victims were disrupted at once, their stars braiding together in a gravitational dance. The implications stretch far beyond our galaxy. If the Milky Way's halo is this littered with stellar debris, other spirals likely are too, meaning galactic archaeology could become a universal tool for unraveling cosmic history. Already, astronomers are using these streams to map the Milky Way's dark matter distribution, since the way they twist and splatter reveals the unseen gravitational scaffolding beneath. Every new stream Gaia discovers adds another piece to the puzzle, turning our galaxy's halo into a sprawling scrapbook of ancient mergers, and the discoveries aren't done. Fainter, narrower streams, some perhaps the remnants of globular clusters rather than galaxies, are still coming into focus. Their stars so sparse they're like tracing individual grains of sand in a hurricane. Yet each one holds clues, whether to the Milky Way's turbulent youth or the nature of dark matter itself. The more we study these stellar splatters, the clearer it becomes our galaxy isn't just a structure. It's a palimpsest, its history written in the faint glow of digested neighbors waiting to be read. Astronomers never expected to find a supermassive black hole sprinting across the cosmos, much less one dragging a colossal trail of infant stars behind it like a celestial bridal train. Yet in 2023, the Hubble Space Telescope captured exactly that. A black hole weighing as much as 20 million suns, barreling through intergalactic space at 4 million miles per hour, its furious exit leaving a 200,000 light-year-long scar of young stars in its wake. This wasn't just a black hole on the move, it was a runaway cosmic titan, rewriting the rules of galactic physics with every light year it traveled. The scene reads like something from a sci-fi novel. As the black hole plows through clouds of gas, its unimaginable gravity compresses the material in its path, triggering bursts of star formation so intense they outshine entire galaxies. Behind it, the newborn stars form an almost straight line, their blue-hot glow contrasting against the void like a wake behind a speedboat. What makes this spectacle even more bizarre is that supermassive black holes are supposed to sit anchored at the centers of galaxies, not go rogue across the intergalactic wilderness. So how did this one break free? The leading theory involves a violent galactic ménage à trois. Simulations suggest the black hole was originally part of a three-galaxy system, where a close encounter between two spirals merged their central black holes into a binary pair. When a third galaxy barged in, its own black hole disrupted the delicate dance, creating a gravitational slingshot effect that ejected one of the trio at breakneck speed. It's the cosmic equivalent of a pinball ricocheting off bumpers, except here, the pinball is an object so massive it warps space-time itself, and the bumpers are entire galaxies. But the real mystery isn't just how it escaped, it's why the star trail exists at all. Black holes are notorious for devouring matter, not nurturing it. The key lies in the extreme conditions of its escape. As the black hole tears through gas clouds, its gravity heats and shocks the material, but its speed prevents it from swallowing everything. Instead, the compressed gas collapses into stars, a process normally seen in galactic spiral arms, not the barren voids between galaxies. The result is a stellar contrail, a freak byproduct of a black hole's chaotic exit strategy. This discovery forces us to rethink black hole behavior on multiple fronts. First, it proves supermassive black holes can be ejected from their host galaxies, something theorists debated but never had conclusive evidence for. Second, it reveals these monsters can become engines of creation, not just destruction, seeding the cosmos with stars where none should exist. And third, it hints there could be more of these runaway behemoths lurking undetected, their star trails too faint to spot until now. Future telescopes like the Nancy Grace Roman Space Telescope will scan for more of these fugitive black holes, potentially uncovering an entire population of galactic outcasts. Each one could teach us about the violent mergers that shape galaxy evolution and the bizarre stellar phenomena that happen when the universe's most destructive objects turn into unlikely midwives of star birth. For now, this lone sprinting giant stands as a testament to cosmic chaos, proving that even the mightiest anchors can be torn loose, and that from destruction, creation sometimes follows. For decades, astronomers faced a cosmic accounting error so glaring it threatened to rewrite the rules of the universe. All the atoms making up stars, planets, and galaxies, what scientists call baryonic matter, only added up to half of what the Big Bang's equations predicted. Where was the rest? This wasn't dark matter, that mysterious invisible substance, but perfectly ordinary protons and neutrons that had somehow vanished from the cosmic ledger. Now, thanks to some of the most sensitive telescopes ever built, we've finally found the universe's missing matter, not in some exotic form, but hiding in plain sight as diffuse, superheated gas strung between galaxies like cobwebs across the cosmos. The breakthrough came when researchers turned their instruments toward the faintest glow imaginable, the soft X-ray hum of oxygen atoms floating in intergalactic space. Using the European Space Agency's XMM Newton telescope, they detected vast reservoirs of gas so hot it emits X-rays, yet so thin it had eluded detection for decades. Imagine trying to spot a single light bulb in a fog bank stretching millions of light years. That's the challenge astronomers faced when hunting these elusive filaments, which form the so-called warm-hot intergalactic medium, or WIM. The gas isn't concentrated in neat clouds but smeared across the cosmic web. the sprawling network of dark matter filaments that connects galaxies across the universe. What makes this discovery so revolutionary is how it solves multiple cosmic puzzles at once. The Big Bang's nucleosynthesis models predict exactly how much baryonic matter should exist based on the light elements forged in the universe's first minutes. For years, the numbers didn't add up. Observations of stars, galaxies, and even the interstellar medium accounted for barely half the expected matter. The WIM neatly plugs that gap, its diffuse gas contributing just enough mass to balance the cosmic books. It's like realizing the loose change you've been missing was scattered across your house in barely visible dust particles all along. Finding these filaments required ingenious detective work. Since the gas is too faint to see directly, astronomers used distant quasars, the blindingly bright cores of active galaxies, as cosmic flashlights. As quasar light traveled through the WIM, certain wavelengths were absorbed by oxygen atoms, leaving telltale fingerprints in the spectra. It's the same principle forensic scientists used to identify chemicals in a lab, only scaled up to intergalactic proportions. Some filaments were even detected by their subtle distortions of the cosmic microwave background, the afterglow of the Big Bang, as their electrons scattered ancient photons like fog bending a lighthouse beam. But the real surprise was just how extreme these environments are. The WIM gas isn't lukewarm, it's searing at temperatures between 100,000 and 10 million degrees Celsius, heated by shock waves from colliding galaxy clusters and the relentless energy of supermassive black holes. Yet despite its heat, the gas is so sparse that a cubic meter of it might contain just a single atom. If you could fly through it in a spaceship, you wouldn't even feel the temperature. There simply wouldn't be enough particles to transfer meaningful heat. It's the ultimate cosmic irony. The universe's missing matter was hiding in the most voluminous yet least dense places imaginable. This discovery doesn't just close a chapter in astronomy, it opens new questions about how the cosmic web functions. The WIM isn't just passive filler, it's the universe's circulatory system, cycling elements forged in stars between galaxies. Supernova and black hole winds blast heavy elements like oxygen and iron into these filaments, where they're eventually swept up by new generations of galaxies. Some simulations even suggest the WIM could contain primordial pockets of gas untouched since the Big Bang, preserved in the voids like amber trapping ancient air. With upcoming telescopes like ESA's Athena mission set to map the WIM in unprecedented detail, we're on the verge of seeing the universe not just as islands of stars, but as an interconnected tapestry of matter, one where the empty spaces between galaxies are anything but empty. The missing baryons were never truly lost, we just needed the right tools and the right perspective to find them hiding in the cosmic shadows all along. From rogue black holes sprinting through space to galaxies resurrected from the dead, the cosmos keeps serving up mysteries that defy our wildest imaginations. Who could have predicted we'd find planets fluffier than cotton candy, or black holes caught mid-escape with trails of newborn stars in their wake? And let's not forget the universe's ultimate disappearing act, those phantom particles called neutrinos, shape-shifting as they dart through your body right now. Just when we think we've got it all figured out, the cosmos laughs and throws another curveball, like dark matter swirling in invisible whirlpools or ancient stellar fossils hiding in plain sight. What's truly humbling isn't just the scale of these discoveries, it's how much more we don't know. For every question answered, a dozen new ones erupt. Are those eerie ORCs cosmic shockwaves or something far stranger? Is the Hubble tension a glitch in our math or a crack in the foundation of physics itself? And what's next? With telescopes like JWST and Roman coming online, we're not just peering deeper into space, we're stepping into an endless labyrinth of wonders where every turn reveals another "wait, that shouldn't exist" moment. So here's the real takeaway. The universe isn't just big, it's weird, and it's alive with mystery. And you're part of the story. Every time you look up, you're witnessing a chapter of a saga that's still being written. So tell me, which of these discoveries left you utterly starstruck? Was it the runaway black hole painting the void with stars, the zombie galaxy cheating death, or something else entirely? Drop your thoughts below. Let's nerd out over the cosmos' greatest hits together. Because the best part of science isn't having all the answers, it's the thrill of asking